my name is Abdullah Giray Yağlıkçı, and I will be presenting our work, BlockHammer, preventing RowHammer at low cost by blacklisting rapidly accessed DRAM rows. I will first begin with an executive summary. RowHammer is a worsening DRAM reliability and security problem. However, state-of-the-art RowHammer mitigation mechanisms face limitations supporting current and future commodity DRAM chips because of two reasons: limited scalability with worsening RowHammer vulnerability and limited compatibility with commodity DRAM chips. The goal of this work is to efficiently and scalably prevent RowHammer bit flips without knowledge of or modifications to DRAM internals. Our key idea to achieve this goal is to selectively throttle memory accesses that may cause RowHammer bit flips. Our mechanism BlockHammer performs three operations. First, it tracks activation rates of all rows using area-efficient Bloom filters. Second, it throttles row activations that could lead to RowHammer bit flips. And third, it identifies and throttles the threads that perform RowHammer attacks. We evaluate BlockHammer's scalability with worsening RowHammer and demonstrate that it is competitive with state-of-the-art RowHammer mitigation mechanisms when there is no attack in the system, and it provides significantly higher performance and lower DRAM energy consumption when a RowHammer attack is present. BlockHammer is compatible with commodity DRAM chips because it does neither require proprietary information of DRAM internals nor modifications to DRAM circuitry. Let me briefly explain RowHammer next. In this figure, we see a DRAM array in which DRAM cells are accessed in row granularity. To access a DRAM cell, we need to open or activate the row which contains the cell. After all requests are serviced from this row, we must close or precharge this row in order to begin accessing data from another row. Due to an increase in cell-to-cell interference, rapidly activating and precharging a DRAM row can result in bit flips in physically adjacent rows. And continuing to access the same row results in even more failures in nearby rows. This phenomenon is known as RowHammer. Now here, we refer to rapidly accessed row as an aggressor row, and the rows containing bit flips as victim rows. There are four high-level RowHammer mitigation approaches today. The first approach is to increase refresh rate, which reduces the refresh window and thus the activation count that an attacker can reach in a refresh window. The second approach is to physically isolate potential victim rows with sensitive data from aggressor rows that a potential attacker can hammer by allocating isolation rows in between. The third approach is called reactive refresh. In this approach, when an aggressor row is hammered, potential victim rows are refreshed to avoid bit flips. And the fourth approach suggests proactively throttling memory accesses such that no row's activation rate can reach RowHammer threshold. Unfortunately, existing mechanisms face two key challenges. Let's begin with the scalability challenge. As DRAM chips become more vulnerable to RowHammer, increased refresh rate requires refreshing all rows more frequently, and it is not sustainable due to large number of rows that need to be refreshed. Physical isolation requires allocating more isolation rows, and reactive refresh needs refreshing more potential victim rows more frequently. Proactive throttling slows down the system furthermore. Therefore, scalability with worsening RowHammer vulnerability is an important challenge for all mitigation approaches. The second challenge is compatibility with commodity DRAM chips. In a typical system, a virtual memory address is translated to DRAM bus addresses such as row and column addresses within the processor. And later on, these addresses go through an additional mapping within the DRAM chip that we call in-DRAM mapping, which is not visible to the rest of the system. This in-DRAM mapping is important for the vendors because it enables circuit design optimizations to meet density, performance, and power constraints, and it improves yield by mapping faulty rows and columns to redundant ones. Therefore, in-DRAM mapping includes insights into chip design and manufacturing quality. And that is why it is proprietary information. Unfortunately, physical isolation and reactive refresh need this proprietary information to identify which rows to isolate or refresh. To address scalability and compatibility challenges, our goal in this paper is to prevent RowHammer efficiently and scalably without knowledge of or modifications to DRAM internals. BlockHammer's key idea is to selectively throttle memory accesses that may cause RowHammer bit flips. BlockHammer consists of two mechanisms, RowBlocker and Attack Throttler. RowBlocker tracks row activation rates using area-efficient Bloom filters, blacklists rows that are activated at a high rate, and throttles row activations targeting a blacklisted row. By doing so, RowBlocker ensures that no row can be activated at a high enough rate to induce RowHammer bit flips. An attack throttler, meanwhile, identifies threads that try activating blacklisted rows and reduces their memory bandwidth consumption by throttling their memory requests. And by doing so, attack throttler greatly reduces the performance degradation and energy wastage a RowHammer attack inflicts on a system. Let me quickly go over the key evaluation results next. To evaluate the performance and DRAM energy consumption, we conduct cycle-level simulations using Remulator and DRAM power for two types of 8-core multi-program workloads. workloads that contain 8 benign applications, and workloads that contain 7 benign applications along with one thread perform in RowHammer attack. We evaluate BlockHammer and compare against 6 state-of-the-art RowHammer mitigation mechanisms for multi-program workloads, when there is no RowHammer attack and when there is a RowHammer attack present. We use 4 metrics in this evaluation to demonstrate the system throughput, job turnaround time, unfairness, and DRAM energy consumption. When there is no attack in the system, BlockHammer introduces very low performance and DRAM energy overheads. And when there is an attack present in the system, BlockHammer significantly increases benign application performance and reduces DRAM energy consumption. We conduct a scalability study with worsening RowHammer vulnerability, again for the cases where there is no RowHammer attack and when there is a RowHammer attack present. For this study, we scaled the RowHammer threshold from 32K to 1K. We observed that BlockHammer's performance and energy overheads remain negligible even when RowHammer threshold is scaled down to 1K. And BlockHammer scalably provides much higher performance and lower energy consumption than state-of-the-art mechanisms when there is a RowHammer attack present. And next, we analyze the scalability with worsening RowHammer vulnerability from the hardware complexity point of view, in terms of chip area, access energy, and static power consumption. We observe that BlockHammer's hardware complexity scales more efficiently than state-of-the-art RowHammer mitigation mechanisms. We provide more analyses and implementation details available in the full paper. First, the paper shares a security proof where we mathematically represent all possible access patterns and show that no row can be activated at a high enough rate to induce bit flips when BlockHammer is configured correctly. Second, the paper explains how BlockHammer addresses many-sided attacks by tuning its thresholds. And third, we evaluate all 4 high-level RowHammer mitigation approaches through analyzing 14 mechanisms from 4 aspects: comprehensive protection, compatibility with commodity DRAM chips, scalability with worsening RowHammer vulnerability, and deterministic protection. We show that BlockHammer is the only mechanism that satisfies all of them. And this concludes my talk. Thank you for your time and attention. I will be happy to answer your questions.